chemically unchange is usually the word of how people describe catalyst. But how is it possible? Well, this is a detail that is not covered in textbooks, and therefore students usually can't fully appreciate the science behind it. And I think that's really a shame, because that is really where the interesting chemistry is. So in this video, I'm going to explain it to you, and by the end, you'll fully understand it. And I'm sure by understanding it, you can, you'll enjoy learning chemistry more, or it's gonna boost your grades in whatever curriculum you do, or you're just interested in chemistry. Okay, let's begin. So today, my example is a homogeneous catalyst. Homogeneous catalyst, and an example of this is Fe2 plus iron 2 ions. Fe2 plus, and in the lab we usually use iron sulfate solution because it contains Fe2 plus ions, and it is stable enough for us, and as well as inert, and doesn't get involved in the reaction. So it's because of these various factors, therefore we chose this particular solution. So today we're going to investigate this following reaction. So it is 2 iodide ions plus a peroxyl disulfate ion turning into a iodine molecule and sulfate ions. So this is a redox reaction. The iodide ions turn into iodine, and the peroxyl disulfate ions turn into sulfate ions. Oops, the camera just fell. Sorry about that. Okay, the reason why we need a catalyst for this is, if you look carefully at the reactants, both of them have a negative charge. And what do negative charges do? They repel each other. And so that is a major factor that causes the rate to be relatively low. So let me write some notes here. So both have a negative charge. And so the problem would be that it is going to repel. Big problem, big problem. And so we chose the catalyst, iron 2 sulfate, aqueous, because the reaction is aqueous. And by definition, a homogeneous catalyst has to be in the same physical state as the reactants. And what is special about this catalyst is it is a transition metal. And a key feature of transition metals is it has available d orbitals. And d orbitals, they are it has a higher capacity of electrons, and because they have similar energy levels, so it is easy, like it costs less energy to give away or gain electrons, and therefore it causes the properties of transition metals that they have a range of oxidation states. Meaning it's easy for them to change charges. So for example, from iron 2 plus to iron 3 plus and going back. And so in this scenario, in this reaction that we're investigating, it acts as a catalyst by undergoing redox reactions. Meaning it gets involved in the reaction, it changes oxidation state, and it lowers the activational energy and acts as a catalyst. Redox reaction. So in the overall reaction, the iodide ions and the peroxyl disulfate ions react directly. But in this case, if we add a catalyst, then we don't. So instead of this happening, what happens instead is a two-step process. So let's split into reaction 1 and reaction 2. So first of all, this thiodisulfate ions react with Fe2 plus ions to form sulfate ions and Fe3 plus ions. So if you look at the oxidation states, right? Okay, so oxygen would have a oxidation state of -2, and since there are 8 of them, so let's say if we do the math, it will accumulate to -16, and the overcharge is -2, so sulfate must have a total, quote unquote, plus 14, and so each of them with a +7 for sulfate, the oxidation state, and for sulfate ions, sulfur peroxyl disulfate ions would have +7, not sulfate. Sulfate is a different thing. Sulfate is this molecule. This molecule is called sulfate. My apologies. So the oxidation of sulfur in this case will be, okay, let's do the math of oxygen, will be -8 overcharge is -2, so this must be +6. So you can see that the oxidation state has decreased from +7 to +6. This means this is a reduction. And I think it's quite obvious from iron because it's just an ion by itself. Oxidation has happened. So within the sulfur molecule group, let's say, let's separate this reaction, let's say, into sort of two different groups. The sulfur group has undergone reduction. So there's this electron donation. So it has gained electrons, and iron has gave away the electrons for the sulfur compounds to gain the electron. So this is the exchange that's happened. In this reaction, we have, so the Fe3 plus has gone from the sulfur reaction from up there down here, down to here. And it reacts with iodide ions, and iodide ions undergo oxidation, and iron ions undergo reduction. As you can see from the charges that they have before this reaction to and afterwards. So the iodine has undergone oxidation because it has given away electrons, and iron has gained it. So this is reduction. And so let's look back at the overall reaction. This is the overall reaction. What just happened is, in reaction 1, one of the original reactants, which is peroxyl disulfate ions, has produced sulfate ions with iron 2 plus being the electron donor. And so sulfate ions is one of the products in the overall reaction if we look back. Sulfur, here we go. So sulfur has been produced in reaction 1, and here iodine is produced in reaction 2. So this is produced in reaction 2. So they are produced in, they are produced in two different steps. You may say, even though it happens in a really fast process, so it seems like it's happening at the same time, but by splitting this instead of these two reacting straight ahead, the activation energy has lowered. And what has happened to iron during the process is iron has undergone oxidation to form Fe3 plus by reacting with peroxyl disulfate ions, has formed Fe3 plus, and then by reacting with iodide ions has formed back to Fe2 plus. So it has remained chemically unchanged. It went back to its original form. So let's do a quick summary. Let me just illustrate this a little bit more in terms of how did the reductions and the oxidations happen. So this is a redox reaction. And here you can see the peroxyl disulfate ions has undergone reduction, and the iodide ions has undergone oxidation. So there's this, that you can say a transaction of electrons from A to B So the electron has been exchanged. It doesn't go both ways. It just goes one way. One donates, one accepts. End of story. And the role of iron is, instead of exchanging directly between peroxyl disulfate ions and iodide ions, what's happened is the peroxyl disulfate ions has exchanged with iron. Iron acts as the lender of the electrons. So in this overall reaction, right, peroxyl disulfate ions, they gain electrons. And so iron gave away the electron first. But ultimately, iodide has to pay back. Like, it's like you borrow from the bank, but you ultimately need to pay back the bank, because if that, ultimately that is what like the transaction is supposedly between peroxyl disulfate and iodide, because that's the whole reaction. But iron gave the electron first, and then iodide paid it back through here. And so iron isn't any end product. Like it is involved in the reaction, but after being involved, it returns to its original state. So at the end of the reaction, it didn't change. It went back to its original state. And that is what a catalyst do. And that is the definition of a catalyst. That is how it works. And you won't find this in a textbook. You'll only find it here. So what the catalyst has done is it avoided the repulsion problem between the two reactants in the overall reaction, because if they're both negatively charged and will repel. Therefore, lower activation energy. One of the key features within the definition of a catalyst. Oops. So, this reaction is usually done in the lab to illustrate rates of reaction. And so, then you need something to measure, because in the reaction you have the independent variable, you have the dependent variable, and you also have the controlled variables. And so, what was a dependent variable? Well, first of all, you need to measure something, but in this case, everything is just transparent. You don't know anything about the rate. So what we do is we add starch. The reason why we add starch is because iodine is one of the products of the reaction. And what happens when starch and iodine mix is it turns blue. And so it's sort of like a clock reaction, or you can think of it as a disappearing cross reaction. Basically, as the reaction proceeds, as iodine is being produced, the solution will turn more blue and blue and blue and blue. And so in this case, you can measure the time when the blue appears. You can, if you're more precise, you can use a colorimeter, where you measure the absorption frequency of the color of the solution. So yeah, starch. Let me just finish the notes. And so this is what they usually do, just to give you a bit of context of this reaction. So obviously, if you compare when the dependent variable is whether catalyst added, for example, then the time taken for blue to appear would be shorter if the catalyst is added, because the activational energy will be lower, and therefore the rate of reaction would be faster. And so to generalize this idea of a homogeneous catalyst speeding up a reaction, with a bit more explaining so that you actually understand what's going on, it lowers the activation energy. Activation energy by iron lending out it's lending out an electron turning into Fe3 plus from Fe2 plus to Fe3 plus, it let out a electron that iodide should have lent out to complete the reaction, but Fe2 plus done it first, because they want to speed up things. Maybe perhaps they want to go home faster. I don't know. However you like to think about it. And then afterwards, iodide pays it back, turns to iodine, and Fe3 plus goes back to Fe2 plus. Understand? So now you know how a homogeneous catalyst works. Congratulations. This is not a easy topic. I hope you have thought well. One of the tougher topics for high school chemistry. Well, I don't know. I don't really know who my audience is. I don't know if you're a high school student or it's just someone interested in chemistry. Please leave any comments of this video, any reviews. Would really appreciate it. And see you next time.